All right, I'm good to go.
Okay, so it's a pleasure to have Thomas Dumitrescu, who's going to speak about two-group global symmetry in 6 dimensions. Thank you very much.
Okay, thanks. Thank you so much for the invitation. It's really a pleasure to finally join you after such a long time of anticipation. And virtually is better than not at all. So thanks for the invitation to speak. I'm going to be talking about a two-group global symmetries in quantum field theory. I'll explain what these are. And concretely, I'm going to do that in the context of six-dimensional quantum field theories, mostly supersymmetric theories inspired by string theory. So this is based on a paper that I wrote last year with Clay Cordova and Ken Trilligator, as well as some previous work and some ongoing work that I may or may not have time to mention. So since I decided to focus on 60 theories, let me give you a little bit of context. I'm sure very familiar to many of you. It's a famous story that if you decouple gravity in various string or brane constructions, you can construct many examples of interacting UV-complete theories in 6 dimensions that are not gravitational, that do not have dynamical gravity. And all the known controlled examples preserve some amount of supersymmetry for various reasons that comes only in 3 different forms. There's the minimal supersymmetric 1, 0 theories, and then there's the 2, 0 and 1, 1 theories. 60 supersymmetry is chiral, so this refers to the chirality of the 60 spinors. Okay, so this is a long and famous and beautiful story that I'll not review in detail, and I'll also omit many references, so I apologize for that. Now, when you take such a decoupling limit, depending on how you take it, the non-gravitational theory you get is typically not a local quantum field theory. Instead, generically, what you land on is what's now called a little string theory. So little string theory is characterized by a mass scale, a little string mass scale M string, and only in the deep IR below that mass scale does it flow to a conventional quantum field theory or effective quantum field theory deformed by irrelevant operators. And we can distinguish 2 scenarios depending a little bit on what this low energy effective field theory looks like at long distances. One option is that the long distance physics is characterized by a superconformal field theory, in other words, by a genuine fixed point of the renormalization group, in which case the supersymmetry must necessarily be of type 1, 0 or 2, 0. This is something one can show. And if you wish to study that fixed point on its own, you are entitled to do so. This is a perfectly good quantum field theory. You can forget about the embedding into little string theory. It has well-defined local operators, and in particular, it has a well-defined local and conserved stress tensor, T. And what makes these theories interesting and challenging is that they're typically strongly coupled, and they typically don't have a Lagrangian description. The canonical method for studying such theories is to analyze their moduli space of supersymmetric vacua, in particular in 6 dimensions, the tensor branch of the moduli space, which is the 60 version of the 4-dimensional Coulomb branch. And on the tensor branch, the theory becomes weakly coupled. It flows to a weakly coupled phase and can be analyzed. Okay, so that's option 1. Option 2 is that the infrared field theory itself, even at the origin, might actually be a weakly coupled quantum field theory. It might not be a strongly coupled superconformal theory. For example, it might be a gauge theory in 6 dimensions. If that happens, then the theory there is weakly coupled and even has a Lagrangian, but it is not conformal. As I'll emphasize in a second, 60 gauge theory is not conformal, and it is not UV complete. So in that case, we are not entitled to study this theory in isolation. We must actually remember the embedding into the little string theory and the modifications that kick in at the little string scale. And these are the 2 different infrared behaviors. Of course, once you go to high enough energy, you really see that the theory is not local. You see the little strings. For example, you see that at high enough energy, the stress tensor stops making sense as a local operator in position space. And you see stringy features like T-duality or a Hagedorn density of states. So I will mostly be interested in the infrared in this talk, but it's good to keep this embedding in mind. And I'll be interested in infrared scenarios of both types, type 1 or type 2, although I'll probably spend more time on type 2 than on type 1. Okay. Now, why am I reviewing this well-known and beautiful story? I'm reviewing it because I would like to re-examine at least a large class of these theories through a different perspective, and that's the perspective of some of their global symmetries, in particular beyond the usual global symmetries that we talk about, like supersymmetry. And that's where the two-group symmetry will make an appearance. And these symmetries will also be closely related to various anomalies in the theory. Okay. So the linchpin for what I'm going to tell you is related to the fact that both type 1 and type 2 theories have infrared phases where they are described by 6-dimensional non-abelian gauge theories. Standard 6D Young-Mills gauge theories. And since we're talking about supersymmetric theories, these sit in some vector multiplets. And as I already said, the 6D gauge coupling is not dimensionless. It has dimension of 1 over energy, and therefore it's irrelevant in the infrared. So 6D gauge theories are IR free. Now, as I said, for strongly coupled superconformal theories, this non-abelian gauge theory description is valid on the tensor branch. But in other examples, like in certain types of little string theory, it's true even at the origin. And what I'm going to say is going to be most dramatic in theories that have such gauge theory phases, although there's a version of it more generally. Now, if you have a 6-dimensional gauge theory, there is an interesting operator that kind of hits you in the face. Given the non-abelian 6D gauge field and its field strength, little f, you can form the standard instanton density. So the second Chern class of f. This is a closed 4 form, right? Just like the instanton density in 4 dimensions. And therefore, its Hodge dual is a conserved 2 form. So I'll call this 2 form J sub instanton, and I'll call it the instanton 2 form. And because it's conserved, it's a current. Right? The star of a closed form is always a conserved form. So this J sub I, this instanton density, is a conserved 2 form current in 6 dimensions. And therefore, you can integrate it to make a U1 1-form symmetry in 6 dimensions. And this is a continuous 1-form symmetry because it came from a current, from a local conserved current. I'll call this the instanton 1-form symmetry. So this symmetry is present in all 6D gauge theories, very similarly to how the monopole symmetry is present in lower dimensional abelian theories. Let me remind you quickly how you get from this conserved 2-form current to the 1-form symmetry. In order to define the corresponding charges, you integrate the instanton density over a 4-cycle, a closed 4-cycle that gives you an integer, gives you the instanton number on that 4-cycle. And there are charged objects whose charge is measured by these kind of integrals. For example, in 6D gauge theories, the uplift of the standard BPST instanton is a solitonic string, and that string is charged under this symmetry. So if you want to count the number of strings, you can integrate that instanton density across the 4-dimensional space transverse to the string, and you'll find the total number of strings. Just like you integrate the magnetic field in lower dimensions in order to count Abrikosov strings in a abelian model. And there are also charged line defects that are operators creating such strings. So this is how continuous 1-form symmetries work in any dimension. Here we're in 6 dimensions. Now, this 1-form symmetry is really a global symmetry. It's not a gauge symmetry. And this is its conserved current. If it is really a conserved current for a global symmetry, it should couple to a background gauge field, a non-dynamical background gauge field. And because this is a 2-form current, that gauge field has to be a B field. So this is by now pretty standard. And so we're going to couple our instanton currents to the B field. And when we write it out in terms of the original instanton density, what we get here is a kind of Green-Schwarz-like term in 6 dimensions that contains the dynamical gauge field little f of my gauge theory and the background B field that I'm using as a source for this current. And it's a standard fact, which is easy to verify here, that current conservation of this two-form current is equivalent to gauge invariance of the background B field. So if I do a background gauge transformation on big B, then this coupling is conserved. This coupling is invariant. Okay, very good. So this is the sort of general thing I wanted to start with. Now I'm going to start looking at a little string theory example that flows to a weakly coupled gauge theory that has this symmetry. So are there any questions before I move on? Okay. Good. So I'm going to start with the maximally supersymmetric 1,1 little string theory in 6 dimensions. And this is one of the original little string theory examples introduced by Seiberg. And this is easy to visualize as the little string decoupling limit of an NS5 braid stack in type 2B string theory. So here's my NS5 braid stack in 10 dimensions. There's a transverse R4. There are n NS5 brains. The supersymmetry preserved by this setup is 1,1 supersymmetry in 6 dimensions. That's 16 supercharges, same as n equals 4 in 4 dimensions, but non-chiral in 6 dimensions. So I have one left-handed supercharge and one right-handed supercharge in 6D, and there's an SU2 R symmetry acting on each of these doublets. So overall, the R symmetry is SU2 left times SU2 right, which combines to the SO4 or spin 4 that rotates the transverse space here in the brain cell. And in the deep IR, this 1,1 theory flows to 6-dimensional maximally supersymmetric Yang-Mills theory with gauge group UN, where n is the number of NS5 brains. So this is just the 6D version of n equals 4 SUSY Yang-Mills, but here it's an infrared-free weakly coupled gauge theory. And I'm going to do the usual thing and forget about the center of mass of this brain stack. So I'm going to drop the U1 and focus on the SUN part. This is not quite correct globally, but it's good enough locally. And that's most of what I'm going to focus on. Okay, good. So I already told you that any 6D gauge theory has a U1 instanton one-form symmetry, and so does this theory. And in this theory, the instantons are literally the little strings. They are literally the infrared manifestation of the little strings in the theory, the heavy little strings. And of course, after the decoupling limit, those are the ones that come from the fundamental type 2B strings. And you can think of the source B2 that we turned on for our instanton density as the decoupling limit of the NS and SB field. Okay, this is a lot of fun, but why is it interesting? What is the story I want to tell about this? Well, what I want to do is I want to go with you through a calculation of the anomaly polynomial of this theory. This is a venerable exercise in field theory and string theory, and we're going to learn something new once we look at the anomalies. So we're in 6 dimensions, and if we're interested in local anomalies, in other words, anomalies characterized by continuous symmetries and conserved currents, then the anomaly is captured by an anomaly 8-form polynomial. So here's my anomaly 8-form polynomial, which is a kind of an 8-form made out of various characteristic classes for both the dynamical and the background fields. And I'm going to look at different terms in this anomaly polynomial and give them some interpretation. So I'm going to call the 3 parts that we're going to discuss in turn I gauge, I global, and I mixed. And these anomalies can be calculated easily from the SUSY Yang-Mills description in the infrared, because they only get contributions from massless particles. Okay, so the contribution of I gauge is by far the most famous and the most familiar. It can be calculated by evaluating a box diagram in 6 dimensions with 4 external gluons. So here I have 4 dynamical gluons on the external legs, which are the particles created by my dynamical gauge field little f. the SUN gauge field. And this kind of anomaly in 6 dimensions can have two different contributions, a reducible one and an irreducible one, corresponding to either C4 or C2 squared. And both of these can be calculated by evaluating this box diagram. So you get two anomaly coefficients here, which I didn't write out explicitly, but these are pure gauge anomalies. These anomalies must necessarily vanish for the theory to even be mathematically consistent. So it is a true fact, and also kind of obvious from various points of view, that the gauge anomalies in this theory have to vanish. One reason it's obvious is because as far as the gauge quantum numbers are concerned, this theory is actually vector-like, it's not chiral. Good. So this theory is a consistent gauge theory in 6 dimensions, which is something we knew anyway. All right, let me move on to the next bit of my anomaly polynomial, which I'll call I global. I global is computed from a similar box diagram with gauginos or fermions running in the loop, but I'm going to take all 4 external gluons and replace them by global symmetry currents. So the anomaly diagram is very similar, but the interpretation is very different. Roughly speaking, all the dynamical gauge fields that appeared here are going to be replaced by background fields. So if you do this computation, you'll find the following contribution to the anomaly polynomial. You'll find a polynomial in all the various background fields. So here, for example, C left is the term class for the SU to the left, and similarly for C right, and P1 is the first part jargon class for the tangent bundle. So here I get some nice characteristic class in terms of the background fields. And anomalies associated to such terms in the anomaly polynomial, which only contain background fields, are now often called Hooft anomalies for the global symmetries of the theory. So the global symmetries are the SU2 left and SU2 right R symmetries and the Poincare symmetry. And these non-vanishing anomaly diagrams tell you that there's some interesting anomalies associated to these global symmetries, but they don't break the global symmetries. Okay? The currents themselves are conserved as operators. If you study the conservation equation of the global symmetry currents inside correlation functions, you will not find any violations at separated points. This is important for a variety of reasons. And the only way the anomaly shows up is either as a very subtle kind of C number contact term, if you really look at coincident points in flat space, or alternatively, you can actually activate the various background fields and see C number violations of background gauge invariance. Okay, so these are very interesting objects, and we like them a lot for various reasons. For example, they satisfy a Hooft anomaly matching, which is an important tool in strongly coupled RG flows, but they don't signal a breakdown of the symmetry in any way. Good. So now I've really contrasted these two extreme cases, the gauge case where the anomaly had to vanish for consistency, and the purely global case, or the Hooft anomaly, which could be non-zero in an interesting way, but did not signal any breakdown of the symmetry, nor any inconsistency. And now I'm going to turn to the piece that I called I mixed. And that is going to be a little bit new. So I mixed, as you might imagine, is a piece of the anomaly polynomial that contains both the dynamical SUN gauge field of the Yang-Mills theory and some of the background fields for the global symmetries. So it comes from a loop diagram, from a box diagram that has two external gluons corresponding to the fact that this C2 of F is quadratic in the field strength. There's two gluons. And two global symmetry currents for the R symmetries corresponding to these C2s here. And if you evaluate this diagram, you'll find this anomaly coefficient. So the C2 left has an n in front of it, and the C2 right has a minus n in front of it. Okay, so the question we must ask ourselves is what to do with this kind of mixed anomaly that is half dynamical and half background. Which camp should it sit in? Does it signal a breakdown of consistency or gauge invariance, like the pure gluon diagram, or is it completely innocuous, like the Hooft anomaly? Well, the first thing to reassure ourselves is that this diagram does not represent a breakdown of gauge invariance. You can, in fact, regulate this diagram in a way such that gauge invariance is completely conserved, and you should do that. You have to do that. You should insist on regulating the diagram in this way. And that actually eliminates all the ambiguity that is typically associated with such anomalous diagrams. So you have to insist on gauge invariance for the dynamical gluons. And then the rest of the diagram is completely unambiguous. And what you learn is that this diagram has a non-trivial effect on the global symmetry currents. It leads to an interesting non-conservation equation. So this is what it looks like. To evaluate the current conservation on either the left or the right R symmetry current, what you find on the right-hand side, right? This is a dimension six form. So you should find a dimension six form on the right-hand side. What you find is the anomaly coefficient, and then a mixture of dynamical operators and background fields. So roughly speaking, what you have to do is you have to apply the descent formalism to this 8 form to extract the 6 form sitting on the right-hand side here. And what you find is C2 of the dynamical gauge field, which is a non-trivial operator in the theory. But this operator isn't there by itself. It's also multiplied by 1 wedge power of the C number background fields for the left and right R symmetries. Good. So this equation, this non-conservation equation for the current, is the consequence of this non-vanishing anomaly diagram. This is just a fact, and now you have to deal with this fact. So the question is, how do you interpret it, and what is it good for? Well, the good thing is that this 6-dimensional anomaly equation is a kind of straightforward generalization of a 4D phenomenon we had analyzed previously. And the correct interpretation of this equation is not that the symmetry currents for the left and right R symmetries are destroyed or broken. So this equation does not mean that the left and right R symmetries are not actually symmetries. That would be extremely weird, since they're manifest symmetries, for example, of the brane construction. And one easy way to see that is that if you want to test whether or not a symmetry is actually a symmetry, you should turn off the corresponding background fields. Just go to flat space, no background fields. And when you turn off the background fields, this term vanishes. So the right-hand side vanishes when you turn off the background fields. And that's a signal that the currents themselves are actually perfectly fine. So they're actually conserved operators, and you can use them to define conserved integrated charges. So this right-hand side does something, but it's more subtle than modifying the charges. Instead, what it does is it modifies the algebra of the currents. So it leads to a deformation of the current algebra. And you can derive that deformation by taking a variational derivative with respect to this background field. That brings down another insertion of the currents. And so you'll get something like a current OPE. And you can even integrate up this divergence to get the full OPE. I'm not going to write it out in gory detail with indices, because these things are, one form and 2 form currents, and they have some structure functions in front of them that are a bit annoying. But I'm going to give you the kind of the main feature of the OPE, which is roughly speaking the fusion rule. So what you learn from this equation is that 2 J left currents, which are ordinary 1 form currents, can fuse into this operator. And remember, this operator is the 2 form current, or the star of the 2 form current of the instanton symmetry, which I call J sub I. So 2 J left currents can fuse into the instanton 2 form current, and the fusion coefficient is this anomaly coefficient N. And similarly, if you take the opposite sign here, you get the fusion of 2 right-handed R symmetry currents into the instanton 2 form current with fusion coefficient minus N. So this is a fusion rule of currents, which is perfectly consistent and which allows ordinary symmetries and higher form symmetries to mix in current algebra. And this is one manifestation of the fact that this theory enjoys a certain kind of global symmetry that is mathematically known as two-group global symmetry. Okay. Now, the usual mathematical presentation of two-group symmetry looks very different from the one that I've given you, but it'll become a little more clear in a second once I discuss the background field. But right now, this is just a phenomenon in quantum field theory at the level of current algebra. So at a very lowbrow level, you could just say that this diagram this anomaly diagram represents a mixing of these two currents fusing into the gluon-gluon operator representing this, this two form here. Okay, now in order to reinterpret this phenomenon in a way that looks a little bit more familiar, what I'm going to do is I'm going to now couple these currents to background fields. So I already reminded you of how to do that for the instant-on current before. So I told you that the instant-on current should couple to a background B field. And of course, we've already implicitly coupled the left and right R symmetry currents to their respective background gauge fields, which are ordinary one-form background gauge fields. And the normal thing to do, without asking too many questions, would just be to shift all of these by ordinary gauge transformations. In other words, these here would shift by D of some zero form gauge parameters, and B would shift by D some one form gauge parameter. Now, if you plug in these gauge transformations here and you integrate by parts to check whether or not the action is invariant under these gauge transformations, you have to use the current conservation equation. That's what we said before. Current conservation amounts to background gauge invariance. But here, the current conservation equation for the left and right R currents is modified in the presence of background fields. It has this non-trivial right-hand side. And because this right-hand side involves the instant-on current, you can absorb this right-hand side by postulating a shift or a new transformation piece in the transformation law for the B field. And this transformation law looks like this. It's a shift of the B field by the field strengths of the R symmetry gauge field in a way that's dictated by the anomaly coefficients. Now, once you look at this formula, you can sort of forget a lot of what I've told you, because this formula is very dramatically recognizable. This formula looks like the familiar Green-Schwarz shift of a B field in string theory. So in other words, the B field B doesn't just shift like an ordinary B field, it also gets this extra shift by the ordinary zero form gauge transformations. And indeed, at the level of formulas, this looks completely identical to standard Green-Schwarz shifts. There is one crucial difference, which is very important, which is that the ordinary Green-Schwarz mechanism is for dynamical gauge fields. So in other words, the B field in string theory is a dynamical field, and the gauge fields are dynamical fields, and everything is a dynamical field, and the gauge symmetry and all the symmetries involved are genuine gauge symmetries. So they're redundancies. Here, we're talking about global symmetries. B and A are background gauge fields, so they're not dynamical. And all these transformations that we are doing are the corresponding background gauge transformations, which are essentially the global symmetries. So the formula is like the Green-Schwarz mechanism, but it's a Green-Schwarz mechanism for background fields. Now, it was appreciated by a whole group of people, starting maybe with Baez and Schreiber and others, that the Green-Schwarz mechanism in string theory could be understood in terms of two-group symmetry. And in that case, that was a two-group gauge symmetry. And similarly, what I'm telling you about here is a Green-Schwarz mechanism for background fields, which is why what I'm talking about is related to two-group global symmetry. Okay. Any questions so far? Okay, so what I've told you so far is, in a very particular example, that mixed gauge global anomalies of the type we encountered in the maximally supersymmetric Yang-Mills theory deform the global symmetry of that theory into a two-group at the level of current algebra. And it's followed from doing this anomaly computation with two global symmetry currents and two gauge fields. Now, it's not difficult to believe that this is very generic in 60 gauge theories. 60 gauge theories are generically chiral. And we saw that this phenomenon even happens in the 1,1 little string theory, or the 1,1 maximally supersymmetric Yang-Mills theory, which is about as non-chiral as it gets. And even there you encounter this phenomenon. So we checked a whole bunch of other string theory examples and found that this phenomenon occurs. And then these authors actually went and did a systematic check of all sorts of examples that have been constructed using F theory, and systematically checked that the vast majority of them have non-trivial two-group symmetry. So the picture that emerges from this analysis is that all little string theories have a one-form symmetry, a U1 one-form symmetry. This is essentially the little string charge, the level of the supersymmetry algebra. And generically, it's part of a two-group. Generically, it mixes with ordinary global symmetries and turns into a two-group. And one thing you can do, for example, is you can match this two-group across dualities. So I said in the beginning that little string theories enjoy dualities, for example, T-dualities, and you can match the two-group symmetry across these dualities. So that gives you a new check of the dualities, but it also gives you confirmation that this two-group symmetry that we found by analyzing the low energy effective quantum field theory is actually a legitimate property of the full theory. Good. So this is the story that I wanted to tell about the string theories and introducing two-group symmetry in that context. In the rest of the talk, what I want to quickly sketch is how this story is modified if the theory that you flow to in the infrared is a superconformal quantum field theory. Can you please remind me how much time I have left since we started a little bit late?
At least 15 minutes.
15 minutes? Okay, thank you.
Where is fine.
Okay, so what happens in superconformal field theories? Well, there's a few things that necessarily happen in superconformal theories that did not happen in the example that we discussed before. And that's going to make a lot of difference. So it's true, and I reminded you in the beginning, that many, many interesting superconformal field theories on their tensor branch have non-abelian gauge fields. So they are effective gauge theories at low energy. However, it turns out that whenever gauge fields occur on the tensor branch of a superconformal field theory, they always couple to the tensor multiplet in an interesting way. So let me remind you that the reason the tensor branch is called the tensor branch is because it's parametrized by the bevs of real scalar fields phi living in a 1,0 tensor multiplet together with some fermions and a chiral dynamical B field. So little b here is a dynamical B field, not the background field big B that we discussed earlier. And all superconformal field theories necessarily have a coupling of this form whenever there's a dynamical gauge field around. So if little f is a dynamical gauge field with second term class C2 of little f, then there's always a coupling of this form to the dynamical B field in the 1,0 tensor multiplet. It looks formally identical to the coupling I wrote down before, but before this B was a background field. It didn't do anything. It wasn't dynamical. Now this little b here is dynamical, and this coupling is much more dramatic. The reason this term is always present in a superconformal theory is because it has all sorts of important functions to perform. The canonical way to explain why this term is always there with non-zero coefficient C is because it's required to cancel certain gauge anomalies, right? Because it's a Green-Schwarz term, it contributes a term to the gauge anomaly, which is effectively the square of this term. So we get a contribution that looks like C times the second Chern class squared to the pure gauge anomaly of the theory. And this coefficient C is non-zero because it has to cancel a certain one-loop contribution involving fermions that gives rise to an anomaly of the same form, but with coefficient minus C. So this is unavoidable in superconformal theories, and this is how Seiberg argued that this coupling has to be there. Okay, so the moment you appreciate that this coupling has to be there, then the role of this current, which before we said was a global two-form symmetry current, changes. If you take a global symmetry current and you couple it to a dynamical gauge field, then it's no longer a global symmetry current. It has been gauged, right? It's like taking a global symmetry and coupling it to QED. The thing that used to be the global symmetry is now the electric charge, and it's no longer a global symmetry in the same sense. So this coupling gauges the instanton two-form current, and it destroys the one-form symmetry that I've talked about in the first half of the talk. So that suggests that this one-form symmetry doesn't actually exist in superconformal field theories. And that interpretation is correct, and you can give a completely independent argument for that. So at the superconformal point, all operators have to sit in unitary multiplets of the superconformal algebra. Depending on how much supersymmetry you have, you might have different algebras. And you can classify all ways in which conserved currents can appear in multiplets, in unitary multiplets of the superconformal algebra. This is something we did in this paper. And what you find is that in 6 dimensions, with any amount of superconformal symmetry, conserved two-form currents like Ji cannot arise. So no unitary 6D SCFT has such an operator, has such a conserved two-form current. And therefore, it doesn't have continuous one-form symmetries like the instanton symmetry. And a fortiori, it does not have the two-group symmetries that involve mixing with this one-form symmetry. So essentially, none of the phenomena that I talked about in the first half of the talk can arise in superconformal field theories. Good. Let me skip this comment about the dilaton. So far from kind of making this case boring, it actually leads to an interesting story. Because I tried to argue before that the kind of mixed anomalies that lead to two groups are quite generic in 6 dimensions, right? They come from these box diagrams, and whenever these anomalies are non-zero, and they are generically non-zero, you have such a two-group symmetry. So now I'm telling you that in superconformal theory, there's some sort of magic where the two-group symmetry always ends up disappearing at the end. So how does this happen? Well, it actually involves a delicate cancellation that allows you to compute certain things or deduce certain things that you couldn't otherwise have deduced. So the absence of two-group symmetries in SCFTs actually has non-trivial consequences. So let me briefly sketch how that works. I already told you that in superconformal theories, the instanton density is gauged by the dynamical B field on the tensor branch, and there's this Green-Schwarz coupling involving only dynamical fields. But because you have the dynamical B field, you can also couple in other Green-Schwarz-like terms that couple to background fields. So B doesn't necessarily only couple to the dynamical C2, it can also couple to a linear combination, suitably quantized linear combination of all the various background C2s or P1s. So for example, here I've sketched the appearance of a Green-Schwarz term involving the dynamical B and the background instanton density for the SU2R symmetry with some coefficient K. And you can include other such terms here. So these are background fields for global symmetries. And this coefficient K is some coefficient that you don't necessarily know how to compute. Some coefficient in the low energy effective action, but it only appears when you turn on background fields. Okay, So what does the Green-Schwarz mechanism do? The Green-Schwarz mechanism tells you that whenever B, which is chiral, remember, couples to something, right, that something squared contributes to the anomaly polynomial. So I have to take this quantity here that I'm circling, square it, and that's the contribution of this Green-Schwarz term to the anomaly polynomial. So when I compute the square, of course, I get the pure gauge term, which we already discussed. I get a pure C-number term, which is in the Hooft anomaly, but I also get a mixed term, right? Because I'm squaring this binomial or multinomial. And the mixed term involves coefficients C and K, and also a mixing of the gauge and global symmetries. So whenever you have such a mixed term, whenever you have such a Green-Schwarz term, a mixed term of this kind is always generated. Okay, but remember that such a mixed term inevitably led to a non-trivial two-group symmetry, right? And I just told you that if you're in a superconformal quantum field theory, there are no two-group symmetries. So this mixing has to cancel, it has to vanish at the end of the day. And the way this happens is that this contribution to the mixing, which comes from this Green-Schwarz term, has to also cancel against one-loop diagrams coming from massless particles in the infrared, right? Just like this contribution to the Green-Schwarz mechanism had to cancel against gauge anomalies of massless particles in the infrared, this mixing, which represents potentially a non-trivial two-group, has to also cancel against massless particles in the infrared. But it cancels for completely different reasons. The reasons don't have anything to do with gauge anomalies. They have to do with the statement that I made before that 6D superconformal theories, unlike little string theories, are not allowed to have these two-group global symmetries. So there's a kind of interesting anomaly cancellation condition which emerges from this condition. And that anomaly cancellation condition allows you to completely fix this unknown coefficient K in terms of pure infrared data that only involves the massless fields on the tensor branch, which you know. In any construction of the theory, you know, in any string construction and field theory construction. Good. So this procedure for calculating these kind of anomaly coefficients like K was proposed a while ago in a paper by these authors. And it was clearly correct, but it was very mysterious. And here you see that the justification involves a somewhat non-trivial argument going by the route of two-group symmetry and its absence. So once you are able to calculate these Green-Schwarz coefficients, you can, for example, compute the entire anomaly polynomial of the UV quantum field theory, with the superconformal quantum field theory, knowing essentially only the massless fields in the infrared on the tensor branch, which is what these authors did. This is, of course, much more than you're typically entitled to. Good. So I don't have time to really explain in detail some of the things that you can apply this understanding to, but let me briefly mention in the last couple of minutes one application involving the a-theorem in 6 dimensions. The a-theorem in even dimensions is the statement that the conformal A-type anomaly of conformal field theory is monotonically decreasing under RG flows. Just realized that my pen stopped working. Okay, maybe I'll stop circling things. So if you have an RG flow interpolating between two different CFTs in the UV and in the IR, then the A anomaly decreases under that flow. And the intuition that goes along with that is the statement that A, roughly speaking, counts the number of effective degrees of freedom along the RG flow. So this is a famous statement in even dimensions, which is a theorem in 2D and in 4D, but not in 6D. There's no general proof of this statement for 6D RG flows, at least not for non-supersymmetric flows. With supersymmetry, you can do better And we had an argument a while back that for supersymmetric RG flows, the change in the a-anomaly is essentially a perfect square and therefore positive. So that implies the a-theorem. However, the a-theorem in itself does not imply, trivially, that the total a-anomaly of a given CFT is positive. Roughly speaking, you might think that it does, because you could, for example, try to take a CFT and flow to a trivial gap theory in the infrared. And if you do that, then the infrared theory doesn't have any a-anomaly. And therefore, delta A is the same as the A of your UV CFT, which is therefore positive by the a-theorem. But in chiral theory, it's not always possible to flow to a gap phase. You might be prevented from doing that by various anomaly considerations. So it actually turns out to be a non-trivial question to prove whether or not six-dimensional superconformal field theories have positive a-anomalies. Okay, so I won't have time to explain a little bit the puzzle that arises in this context, but let me just say that this question can be answered if you have exquisite control of the Hooft anomalies of the theory. The reason is that there's a universal formula that relates the a-anomalies to Hooft anomalies for the global symmetries, in particular the R symmetries and the diffeomorphism symmetries, just like in 4 dimensions. And if you control well enough the Hooft anomalies of your theory, you also control the a-anomaly. So you can prove bounds on A and delta A if you can do that. And what I essentially explained to you previously is that the absence of two-group symmetry in SCFTs gives you a sharp way to calculate all of its Hooft anomalies in Green-Schwarz terms. And so that translates directly into the ability to compute the a-anomaly of the 6D theory, and it turns out you can give a nice and relatively easy proof that it's always positive. So since I'm out of time, I'll stop here. Thank you.
Any question?
I maybe have a naive question. Thanks for a fantastic talk. I was curious if you had any interpretation of what such a two-group symmetry is telling me, or like in particular, it's coming from this OP of R symmetry currents, if I remember correctly.
More generally, it could be any standard one-form current fusing into a higher form current. Yeah.
But if I think, for example, about like a brane world volume theory, then I have sort of a geometric idea about what those R symmetry currents are doing, or what symmetries they generate. I guess I was wondering if there's any sort of geometric intuition, like for example, just in that case, for what this two group is about, or what this deformation is telling me about the string background.
Well, so I can give a few very lowbrow answers. You might be asking for something more sophisticated, which I would also like to know about. But the lowbrow answer is that the two group is not a modification of the symmetry at the level of charges. So if you look at the commutators of charges and the symmetry algebra, it does not appear to be modified.
Yeah.
Okay. So the R symmetry, for example, still looks like it's SO4 and it doesn't look like anything funny is happening. So instead, this is a modification of the current algebra. So in order to detect it, you need to ask some slightly more local question. And there are many ways of asking such a local question, for example, looking at the OPE of the currents, but a different way of asking the question is to actually turn on a non-trivial B field. And when you do that, right, as is familiar from the string theoretic Green-Schwarz mechanism, when you turn on a non-trivial B field because of this transformation rule, it'll mix with the A field. Okay, so if you allow yourself to study configurations where these fields are turned on, you will see this mixing. And of course, in a given string construction, this might be very, very obvious. For example, in the brane construction I reminded you of for the 1-1 little string theory, right? I said that the B field was the actual string theoretic B field, and this Green-Schwarz shift is actually the string theoretic Green-Schwarz shift.
Sure.
The only thing that happens in the decoupling limit is that they get frozen and become background fields. So any intuition you can derive from that, you can transplant to this case.
Sure, okay, that's helpful. Thank you.
Any other question?
Can I read a failure of associativity in the current algebra on in this deformation? Is it like a failure of associativity or of a Jacobi identity, or?
Yeah, so it's not the Jacobi identity for charges. As I said, the algebra of charges is not modified, but there is a failure of associativity if you ask a sufficiently refined question. So you might be referring to the fact that two groups in general are characterized by a non-trivial associator. And you can see that here as well. If you wish, it's all encoded in the OPE of these currents. But if you want to see the actual associator, what you can do is you can integrate the currents to make charges. But then you don't just study the Jacobi identity. What you have to do is you have to study certain F moves, where you move several symmetry surfaces past each other. And if you do that in two different ways, right? The way you usually try to derive the Pentagon identity, and then you'll see the associator come out. And the reason the associator comes out is because as you move these surfaces past each other, at various points they'll intersect, and at the points of intersection, the right-hand side of the current algebra will kick in. Right, precisely when the two currents collide, the two surfaces collide, then you can have an effect.
Other question? All right, so if there are no further questions, I thank again the speaker. Thank you very much.
Thank you.